Today I'm chatting with Professor Shiraz Minwalla. He's a theoretical physicist working on string theory, quantum field theory, and the deep connections between gravity and fluid dynamics. So, Professor Minwalla, welcome to the podcast.
Thank you.
So, before we get into theoretical physics, I want to go back to the very beginning, the history of string theory. Because most of the breakthroughs in the physics are not the work of one person, they are the group efforts built over decades. So, how did this string theory, actually start?
Okay. Now, any discussion of history is always difficult because one tends to oversimplify a lot. With that caveat, let me say, um, it's especially difficult when you have not been around for that history. So you've heard stories and you don't really know how accurate they are. But with that caveat, let me say, um, well, in the 1960s, particle accelerator experiments were finding very confusing data. And the data included a bunch of resonances. Now, at that time, theoretical physics was extremely confused. Theoretical elementary particle physics was extremely confused. It was a time in which even the formalism of quantum field theory was not universally accepted as being the correct formalism. The standard model of particle physics, the current widely accepted theory of elementary particles, was not invented then. And okay, so how to organize this data was very confusing. Now, in particular, the part that was most confusing about this data, one part that was very confusing about this data, was the part having to do with the strong interactions. So when people did scattering experiments, they saw these things we call resonances. So like particles that don't live forever, that are created and then decay. And they found a certain pattern of resonances. Today we understand that pattern of resonances is a consequence of the strong interactions, the QCD, the quantum chromodynamics. These are meson-like states or global-like states, and mainly meson-like states in QCD. However, at that point, QCD wasn't invented. The basic underlying theory was not understood, so it was all very confusing. What are all these resonances? And a bunch of physicists tried at that point to find a way of thinking of the problem that was sort of new. The new way of thinking was, let's forget about an underlying theory. Let's just write down an S matrix, so the rules for scattering of particles, and look at all the constraints that S matrices obey. So there are many constraints that follow from general principles, analyticity, causality, more or less the same thing, unitarity, and so on. And what people did was to try to write down sample S matrices that the hope was that just consistency would completely determine the QCD S matrix. Now it sounds almost ridiculous, but the hope was that QCD S matrix would be determined almost completely by consistency. And people wrote down these S matrices. They wrote down all. They looked at constraints and so on. And then Veneziano, and then other people, Virasor and Shapiro and other people, found sample S matrices that looked really nice. That looked like S matrices that obeyed all known properties in a certain approximation. And they were hopeful, had many of these resonances. They were hopeful that these S matrices would describe the resonances that people saw in particle accelerator experiments in the real world. Now, a few years passed, and then QCD was invented. Asymptotic freedom was discovered. People realized that QCD was the thing that gave rise to these resonances, was just quantum field theory. And so for a while, it began to seem that program of trying to find these resonances from consistency was a little silly. We've got quantum field theory. We understand these resonances. Okay, in principle, understand these resonances. So, however, other people started trying to understand. There's this beautiful formula, the Veneziano formula and Virasoro Shapiro formula for these S matrix. People started trying to understand what kind of physics underlay that S matrix. and realized the following. They realized that you could get that S matrix out of quantizing strings. Now, so that was in some sense the birth of string theory. Now, fast forward to QCD's been doing so well. It seemed clear that one way of understanding strong interactions was just ordinary quantum field theory. Around the same time, other people, Schwartz and friends, realized, and Unea, but okay, so I won't take names because I'll get it wrong. But okay, people realized that one of the properties of these string-like S matrices is that there's a graviton. So the spectrum of string of these the things that you get by quantizing strings, or the spectrum of these S matrices that I told you about, always included a massless spin 2 particles, a graviton. And then the hope was that, okay, this structure, which is not needed for QCD because we've found a quantum field theory, will actually then represent the scattering of gravitons. And so that turns string theory into an attempt to find a theory of quantum gravity. The last thing I'll say, sorry for the length of this answer, but the last thing I'll say is, like, coming back in 1997, Maldacena found the ADS-CFT correspondence, and it's like a grand circle, because one thing that the ADS-CFT has taught us is that you can do both. A theory of quantum gravity in a bulk can also be a theory of strong interactions on the boundary. And so the origins of string theory from studying strong interactions were likely not a coincidence. The fact that a theory of gravity is also a gauge theory is probably a lay behind how string theory was discovered.
So you can say trying to fit gravity into standard model.
Not exactly. Not exactly. Let me say it again. String theory was really born. Veneziano didn't care about gravity. He was not thinking about gravity. It was really born as an attempt to understand strong interaction, what we would today call strong interactions, the spectrum of resonances that we see in particle accelerators experiments. Okay? When people realized that those resonances have another description through ordinary quantum field theory. They realized this. The second thing they realized was that the scattering amplitudes you find from quantizing strings always have a graviton. So it seemed like there were two reasons to believe that that string theorists then were doing the wrong thing. You wanted to find QCD, but A, there's another theory that produces QCD, and B, the theory that you produce has a massless spin 2 particle, which QCD doesn't have. So then people shifted attention to using that as a way of trying to find a quantum theory of gravity, and indeed a theory that would eventually unify both QCD and weak interactions and everything else with gravity. But in the origins, it was just an attempt to understand a quantum field theory. Okay, the hope was that string theory would be a way of understanding that quantum field theory. People realized then that it went into a theory of gravity, and now through ADS-CFT we understand how both could be correct. Sorry again if it's too confusing.
So I want to ask something which a lot of people wonder about, like, including what we hear in mass media and popular science. Why is string theory so hard to prove experimentally? Like, why does it remain just mathematical equations?
The thing about string theory is that it's motivated by the desire to understand the quantum theory of gravity in the universe in which we live. Okay, that's the motivation. The problem with this motivation is that there's almost no experimental data. Okay, if traditionally in physics, if you want to understand a phenomenon, you have access to a lot of experimental data, and that helps you a great deal. At the moment, what we have is the current situation, more or less, is that almost every particle collider experiment we've been able to perform is well expressed, well understood within standard model of particle physics with some additions. And neutrinos have mass. Okay, so what? Similarly, in cosmology, cosmology, when I was doing my PhD, was almost not a precision science. Now it's become really precise, right? And there's a lot of precision data available, and cosmology more or less fits simple equations, more or less. Not completely. There is this Hubble tension that people talk about, And if it survives, might be saying something. But more or less, it's simple, simple. Okay, so we're in a situation where there are almost we've got a lot of data, but almost all of the data is well explained by old models of physics. Okay, so you might think, well, if that's the case, maybe the old models are all that there is. Maybe there's nothing new. But we know that that's not the case. And one great way we know, well, there are two reasons to know that that's not the case. The first is just practical. Experimentally, by looking out into the universe, we know that there's dark matter. Now, dark matter in models of cosmology can be modeled by adding a term in some equation. We know it's there because we can see it clump. It's not just some mistaken equations, because you can map out the dark matter. You can see it clumps here, it goes there. Okay, so it's there. We know that. And our models of particle physics do not have a candidate particle that is the dark matter. So clear ways of missing something just from dark matter. Second, there's dark energy. The universe is accelerating. That can once again be modeled by a term in Einstein's equations, maybe, if the acceleration is not itself accelerating or slowing down or whatever. But maybe it can be modeled by a term in Einstein's equations, phenomenologically. But to make a quantum theory that gets these numbers extremely unnatural, because when re-expressed in terms of the Planck scale, the natural dimensionless length scale and natural dimensionful length scale in gravity, this cosmological constant, depending on how you count it, is like 10 to the power 120, something like that. 10 to the power 120 orders of magnitude smaller than you might naturally expect. It's a very small cosmological constant, which is basically another way of saying that we live in a very big universe. The cosmological constant sets the size of the universe. And okay, there is a natural length scale in gravity, the Planck scale. And if you knew nothing else, you would say, well, if you've got a quantum theory of gravity, what would its size be? Well, it would be the Planck scale. Clearly, we're not living at Planck scale, right?
Yeah.
That's really tiny. Nothing. So the question. So now you could imagine somehow that you had some clever idea, let's say supersymmetry, something like that, and that makes the cosmological constant zero. For a long time, when I was doing my PhD, people believed the cosmological constant was zero. Now, there's good evidence that's not the case. The universe is expanding in an accelerated way. So, however, the length scale, the dimensionful scale that sets that acceleration is very, very small in natural units. Where does that come from? How do you need you need some theory for that? You need some way of understanding that is not, a small correct. You do a calculation, it gives this number. A small correction might change it by a big deal. You need some way of thinking of that. So that's one issue. That's another issue. And finally, there is the question of what is the theoretical framework within which you can do quantum calculations using gravity? Now, there are very few practical places for which this question becomes important. One of them might well be the early universe. If we ever want to know if we're serious about wanting to know the answer to the question, where did our universe begin? How did it begin? What happened? What happened in detail? It seems reasonably likely that we will want to, seems it seems plausible that we would need a theory where you can mix quantum mechanics and gravity. We don't have that. So these are the three kind of broad theoretical motivations for the question. But you see, the kind of data we have is rather vague. We know there's dark matter, okay? We know there's dark energy. And we know that we need to put these things together. But the kind of data that's useful is a bunch of precision numbers. Lots of numbers, then that helps you. Here, these are rather vague things. Very few numbers. So what we're trying to do is to understand the theory of quantum gravity with almost no guidance from experiment. Okay. And this is what makes it very difficult. Now, so what have physicists tried to do? There are two reasonable options at this point. A, you give up. You say, well, let's wait 1,000 years, then we'll have more experiment, then we'll attack the problem. And that may be a rational thing to do, but that's not how humans are. Right? We don't want to solve something 1,000 years from now.
We cannot stop here.
Yeah. So what do you do? Well, what the strategy we've adopted is this: that you see, finding the theory of quantum gravity in the real world without experimental data sounds very difficult, but we'll try. But how do you try? You try by making toy models. You look for any quantum theory of gravity that you can construct. And we're lucky in that consistency plays a big role in constraining these theories. It's much harder to construct quantum theories of gravity than was to construct quantum field theories. For instance, in quantum electrodynamics, the electron has a certain mass. Mu1 has another mass, let's say. Okay. If we wanted to, we could change the ratio of the mass of the muon and the electron. Nothing would go wrong conceptually in the quantum field theory. Okay. Okay. On the other hand, or similarly, there are many such things. You can change masses around, couplings around in some rather free way in quantum field theory. Now, in string theory, as far as we can understand, if we take all the particles, the spectrum of particles we get in string theory, we keep all the other masses fixed and we change the mass of one. Just doing that would make the theory become nonsense. It would violate unitarity, and so the theory would not be right or wrong at that point, it would just be nonsense. So string theory is very tightly constrained by consistency. And that's a great thing, because without that, we wouldn't have known how to start. Because it's so tightly constrained by consistency, you try to look for any solution of this problem that keeps consistency. And that's what string theory is. It's an attempt to find any solution, any consistent quantum mechanical theory that reduces to gravity at long distance. At least in practice, that's what string theorists have been able to do. And by doing this, we've learned a great deal. ADS-CFT, black hole entropy, that kind of thing. We've learned a great deal about general questions that will exist in any quantum theory of gravity. Oh, we've learned a great deal about the structures of theoretical physics. Who would have thought that the best way to do a calculation in hydrodynamics would actually be to do a calculation in gravity? But it's true. So we've learned a lot about the structures of theoretical physics, and we've learned a lot about specific toy models. But in the absence of experimental data, or in the absence of another really great idea, we have not, and it's not clear to me how we will in the near future, made progress in finding the theory of the world in which we live. That has been our shortcoming. Our strength has been that we've learned lots about structures and about general questions. The question of finding, but always in toy models. Like we discussed at the beginning, ADS space is special partly because it's very highly supersymmetric. That very high degree of supersymmetry makes it easy to study. So it's a toy model that is easy to focus on. Okay. So now we focus on this toy model, we learn a great deal from them. And that toy model actually makes, in some sense, contact with experiment. For instance, people who model hydrodynamic flows in LHC now use insights obtained from the fluid gravity correspondence obtained from string theory. Okay, so in some way it feeds into experiment in a minor way. But the question of finding the theory of quantum gravity in the real world, for that won't be good enough to look at toy models. We'll need to work with a model, with a part, the vacuum of string theory, assuming that's the right way to think of it. The vacuum of string theory that actually describes the real world. Then we find it. We have to be able to study it. We have to know why that is, what is special about that vacuum rather than anything else. That part we've not made progress. So we're at a very preliminary stage. We're doing toy model physics. It's a little like finding, instead of understanding, let's say you were interested in understanding a particular phase transition. All you could do is to understand the Ising model. This phase is very different from the Ising model, but you've understood toy models. You've understood the nature of phase transitions. You still haven't understood the theory of that phase transition. So a little like that.
So toy models are not real, but they are not real universe, but they teach us something very important, fundamental how this thing works.
Exactly. They give us insights into the structures of physics, and in the case of string models, they give us qualitative information about how things work. For instance, black hole entropy, how does it work? Black hole information problem. Things that are qualitative and will likely extend across many different. But and that's the nature of toy models, like Onsaga's solution of the Ising model, solution of a toy model, but it's had enormous impact on theoretical physics. Because once you understand some model really well, you understand how things can work, and then going to other models is is easier. But unfortunately, so far, in my opinion, we're at the toy model stage. Some point we want to go beyond that. And that may require new ideas, maybe some new input from experiment. Let's see.
So we are just behind by technology.
Well, yes, hopefully, yeah, or maybe some really good idea. It could be that somebody comes up with a really good idea.
Now, two terms keep coming up in our conversation that I wanted to understand better: CPT and ADS. So I asked Professor Siraj to explain both of them for anyone watching.
CPT, okay. The CPT theorem is the statement that uh, every quantum field theory, and also, as far as we can tell, string theory, um, is invariant under a symmetry in which you do a parity transform, a time, take time to minus time. Parity is taking, let's say, x to minus x, and also do what we call charge conjugation, which is switch the sign of all charges in the theory, take positive to negative charges. Okay, and in particular, this CPT operation will take a particle to an antiparticle. Now, that this is the case is like a very very it's somehow very built into the structure of quantum field theory, and string theory seems to respect that very strongly. I mean, we've seen no sign that it violates that, but also it's seen no sign that it explains it. It's already got an explanation in some sense within the structure of quantum field. Maybe that will change. Okay, let's see people. ADS. Okay, a completely different thing. So ADS is a space-time geometry. So let me describe ADS 5. So as you know, within the theory of general relativity, the geometry of space-time is dynamical. It's variable in the problem. Okay, so when you've got a theory of gravity, knowing its geometry is part of knowing the solution of the theory. So there are some theories of gravity, theories which admit a consistent truncation to Einstein action with a negative cosmological constant. That's just technical verbiage. Some theories of gravity which admit very simple symmetrical solutions. Okay, there are some theories of gravity that admit very familiar simple symmetrical solutions, just flat space. But if your theory has a cosmological constant, flat space is not a solution to the theory. And the simplest symmetrical solution is a space-time that you can think of as, in some sense, in the following terms. Suppose you had, you want to look at a very symmetrical. Suppose you have a 5-dimensional sphere. Okay, so what is that? A 5-dimensional sphere is the locus of all points equidistant from the origin in the space R6. Okay. Now, what's special about the 5-dimensional sphere is that this sphere preserves the rotational invariance of R6. You take R6 has this rotational invariance. Now you take an arbitrary codimension 1 surface in R6. And you try to rotate a point on the surface, you'll rotate a point off the surface. So if you stick to a particular codimension 1 hypersurface in R6, if you choose a generic one, you'll have broken the rotational invariance, because while R6 has this rotational invariance, the surface doesn't, because rotation takes points on it to points off it, or points off it to points on it. However, that's not true of the sphere. You take to rotate on a point on the unit sphere, come back to a point on the unit sphere. So it's a codimension 1 submanifold of R6 that preserves the SO6 rotational invariance of R6. Now, some of your viewers will be familiar with the special theory of relativity, and will be familiar with the fact that in the special theory of relativity, we deal with a flat spacetime.
Yeah.
With one difference, that one of the coordinates in the space has a negative component to the matrix. So the rotational group SO4 of R4 is replaced by the rotational group SO3, 1, which is the group of all rotations that preserves a metric which has diagonal and has 1, 1, 1, minus 1. So now, in the same way, take R6 and replace it with a spacetime that has a metric 1, 1, 1, 1, minus 1, minus 1. 4 space and 2 time directions. Okay? That spacetime has an isometry group, a group of rotation, that is SO4, 2. Now you can ask, does there exist a surface in the spacetime, a codimension 1 surface in the spacetime that preserves this whole rotational group? You know, when I say a rotational group, it's really some of these are rotation, some are boosts because there are some time direction. You can ask, does there exist a surface in the spacetime that preserves this whole isometry group, SO4, 2? And then it does. Now, this surface is not like a sphere. It's sort of like a sphere in R4. There's an S3 inside. But because of these other directions, it's S3 and an S1 and a relative direction of how big the S1 and the S3 are. And if you draw it in R4, 2, it's like a funnel. It goes out all the way out to infinity. Okay? And this almost like hyperboloid. And this space is ADS5. Okay. Now, the important thing about ADS5 is that it is a solution of Einstein's equations. It's a very symmetrical solution of Einstein's equations with a negative cosmological constant. But the thing that made it really important in physics is Maldasena's discovery of the ADS-CFT correspondence, which tells you that some theories of quantum gravity on an ADS-like space are actually just a reformulation of quantum field theory that lives in one-dimensional lower. So in ADS5, it would be a 4-dimensional, 3 plus 1-dimensional quantum field theory. And this quantum field theory lives, in some sense, on the boundary of this space, that space-time. And this is remarkable discovery. And one of the most, possibly the most interesting advance in theoretical physics in the last 30 years. Okay. Please tell me if you'd like me to say more about any of it.
Like how you visualize this ADS space.
How do you visualize the ADS space? Okay. So for different purposes, you visualize it differently. One of the things about this space-time is that when you write it in coordinates, so good. So I told you that there was this R4, 2, which had 2 times and 4 space. But then you've got this hypersurface in the space. So now if you look at the set of all possible hypersurfaces, there are 2 reasonable options. The hypersurface could have both of the time directions and 3 space dimensions. So it could be like R3, 2. Or it could be R4, 1, 4 space and 1 time. The ADS is of that second sort. It has 4 space-like directions and 1 time direction, which is good because when we want to do physics, we do physics in a space with 1 time. So there can be other mathematics, but physics, as far as we understand, is 1 time. So this space now is a space-time which has 4 spatial directions and 1 time direction. Now, to visualize or to be able to work with the space-time, what I usually do is to work with coordinates. So I choose my favorite coordinates and then look at what the metric looks like. So one of the things that happens in this space-time is that the metric in the time direction, the coefficient of the metric in the time direction grows as you go away to the boundary of the space. Now, if you think about redshift physics, that tells you that something with a given proper energy becomes carries very high global energy as you go to the boundary of space. So this is a space where things if you send things far away, that they pick up a lot of energy. Now we're used to that kind of thing, like in a harmonic oscillator. You send something far away, that picks up a lot of energy. So roughly speaking, the space-time is like that. It's the effect of this geometry is to keep particles confined within a region. So for many purposes, you think of it like a box. You think of it like, at least I think of it like a box. Okay? For many purposes, I think of it like a 4 plus 1-dimensional box. But it's a floppy box. It's not like, there's a wall. If you really want to, you can go far, but you pay a price. For many other purposes, you think of it differently. But you have various, the way you get used to thinking about things is to do a lot of calculations. Then you have various different ways of thinking. For some calculations, one way of thinking is good. For other purposes, another way of thinking is good. For some one way of thinking is just as this hypersurface in this R4, 2. For some purposes, that's a very easy way of visualizing. For instance, if you wanted to visualize ADS2, okay, you could visualize this as this hypersurface in R2, in R2, 1 and 1, 2, and then you could really visualize it that way.
So how you choose these dimensions that decide this?
How did I choose this dimension? Well, you see, in general, the rule is Rn, 2, the appropriate hypersurface in Rn, 2 describes ADS n plus 1. So when I wanted ADS 2, I chose R2, 1. Just that. So there was n was 1 then.
So this is something about symmetry.
Yeah, symmetry plays a big role, but it's not just symmetry. These are very the fact that it's a solution of the appropriate Einstein equations is a very important point. That's a solution of equations. Now, but yes, your question about symmetry is certainly on point. In particular, one of the things that these solutions of supergravity or string theory have in them is that they preserve a lot of supersymmetry. They preserve 32 supersymmetries, which is as large as the largest amount, that at least we have experience with. Some people will claim it's impossible to get larger. So it's even more symmetry than what you see visually. These fermionic supersymmetries are a key to making these spaces really good to work with.
So the fact that it preserves so much symmetry, especially supersymmetries, that's why it makes this very special kind of space-time.
Yes, exactly.
So your work is like related to fluid dynamics. Then that connects to it.
Yeah. So the fluid gravity correspondence, which you're referring to, is the following. You can understand this very simply. Hydrodynamics is a very general theory. The basic idea of hydrodynamics is this. You take a quantum field theory, any reasonable system. Okay, but let's say quantum field theory, and you heat it up so that it's in a fluid phase. Now you start it in some state that is completely arbitrary. Now, field theories, all reasonable physical systems, try to tend towards equilibrium. Okay, so you start with some arbitrary state with a lot of energy in it, a lot of stuff in it, and it tries to move towards an equilibrated state. Now, typically speaking, systems have an intrinsic time scale set, for instance, by the local value of the temperature, local value of the energy density, which determines how fast a little lump can move towards equilibrium. So let's call that time scale tau. So we've got some time scale tau, which is determined by local energy densities. This little lump of stuff becomes equilibrated. But now take another little lump of stuff far away. That also equilibrates in that time scale. But to get that far lump to equilibrate with this lump takes time, because things have to move between here and there. So if you're in a big system, there's a separation of scales. There's this tau, which is a time scale in relativistic theory. That's also a length scale, which determines local equilibrium. And then there's the size of the system, which is the size over which something has to equilibrate globally. So if this local equilibration happens before global equilibration, then the subsequent dynamics can be formulated in thermodynamic terms, but thermodynamics made local, where the degrees of freedom of the equations you have to keep track of stop being the particular values of positions and velocities or whatever fields of your specific system, but just become the temperature and the fluid velocity of everything that's moving. And a very good approximation which you can quantify. Keeping track of these makes a closed dynamical system. That's the theory of hydrodynamics. So basically, any system forget about details, under appropriate conditions, when it's high enough energy density and, big enough, it's described by the system equations of hydrodynamics. So this is a general claim. Note that at leading order, the hydrodynamics are classical equations, just differential equations. Okay, unlike quantum field theory, which is not classical equations, it's path integrals. Things are fluctuating. Okay, this is claim one. Now, claim two is Mulder-Seno. Mulder-Seno claimed that in n equals 4 Yang-Mills theory, some particular field theory, in the large n limit, some particular limit, is well described by the classical equations of Einstein gravity in AD as 5 times S5. So now there are two separate claims about quantum field theories. One is that every quantum field theory under appropriate conditions is described by the theory of hydrodynamics. The second is Mulder-Seno's claim that this particular quantum field theory under particular situations is described by another set of classical equations, both classical differential equations, the equations of Einstein's general relativity. Now, these claims are both true, then it might seem that it must be that there is some limit under which these classical equations of gravity reduce to the equations of hydrodynamics. That limit should be when your system is big and you're at high temperatures. And this is what we showed was indeed the case. We showed this was indeed the case by very roughly the event horizon of the black hole becomes local and plays a big role in this correspondence. Very roughly, the fluid is mimicking the dynamics of the event horizon. And that was sort of nice. It was cool that the dynamics of black holes in this way just reproduces hydrodynamics. And surprisingly enough, it taught us a lot about hydrodynamics. Many things that people had said about hydrodynamics, 200-year-old subject. One that people
it's a classical theory, so very old.
Very old, and people have been interested in forever, and people of various different branches of physics and biology and everything are interested. So you might have thought there was nothing new to learn about hydrodynamics.
So underlying theory is quantum, but more about it's large scale. It's effectively classical.
Exactly. Yeah, exactly. And so one. People had done, in the case of relativistic hydrodynamics, very beautifully summarized in this lovely textbook of Landau and Lifshitz. The way people study hydrodynamics is to write down the equations and impose general consistency requirements. And they write down the most general kinds of equations that can appear subject to general consistency requirements. Now, Landau and Lifshitz, in particular, studied the motion of a charged fluid at first order and derivatives, and claimed to have the most general hydrodynamic theory there. This was widely used. This was widely accepted. When we did these calculations within gravity, we found the effect of hydrodynamic equations and we published. We didn't know very much.
So you started your journey at Kanpur, and then you went to Princeton, and then you taught at Harvard. So like the environment difference doing physics there and doing physics here.
Yeah.
Like, does that affect doing physics?
Yes, it does. There are big differences. Well, let me first talk about the things that are not different. If you are in I work at TIFR, which is perhaps one of the best places physics in India, and it's just great. So the environment is really good. The support is really good, meaning you don't have to. You're supported. In the sense of you get your salary, you get a nice place to work, you have a lot of students around you have a lot of postdocs, and the atmosphere in some sense is really good. There's almost no, at least if you want to stay out of it, there's almost no politics. You just do your work. So in some sense, and the environment is very interactive. So in some ways it's very similar. But if I were to compare TIF and Harvard, there are two big differences. I mean, the main one is this. There's just much more money there. Because there's much more money, there are many things that happen that don't happen here. So, for instance, the years that I was at Harvard or at Princeton, every week there would be 3 or 4 people coming through. There'd be somebody coming to give a seminar, somebody coming for some other reason. Maybe 3 or 4 is an exaggeration, maybe 2 to 3 people coming through. Now, these people would come, they would give you a talk, they would be around for a few days, you'd go for lunch with them, you'd go to their office, you'd discuss. And so these are all very good people, So just by being there, you get many new ideas from discussion. You hear what other people are doing, and without any effort, you stay on the top of the field. Anything interesting that's happening in the field, somebody will come by and tell you about it. And you will discuss, and you will attack it, and you will learn something, and you will have your own way, and maybe there's a chance for collaboration there. So I would say that is the single most important difference. The fact that there is this traffic of people, at least the time that I was there was this traffic of people coming through, all really excellent people. Okay, that I would say is difference number one. And this, of course, is just a matter of money. Because if you have enough money, that you can easily do that. Okay. That is, we try the same in TIFR, but it's much less. We have a certain flow of people from India, and also we have a certain flow from people from outside. But of course, it happens much less, partly because of geography. It's a long travel to Europe or America, partly because of money. At some point, it's expensive. This is difference number one. The second difference is that if you're at Harvard or at Princeton, there are some really eminent people around. There are very good people in India. And of course, okay, there's one really eminent person in India like that, as Ashok said, as eminent as anyone else. But there are several of those around in your institute. Okay, so for instance, if Maldacena, Strominger, Seiberg, Witten, that you run your ideas by them, they will say something. Somehow that's very useful. Okay. So these are the two big differences. The last thing I'll say about that is that second thing is a double-edged sword. Because what might happen is that if there are people you respect very much, you take an idea and you start talking to them, and they don't think that, say, somebody thinks, okay, it's not going to work. Then you get discouraged. So, and sometimes you have an idea that you cannot quite verbalize. And the way you say it makes it sound a bit stupid, but, there's something in your head that feels this is something that's interesting here. And at that stage, it may not be too useful for you to get discouraged. You may want to think it through for a while, be able to say it properly, and then you realize that it's something. So I feel that not having those very eminent people around, the people who you respect very much around, also has some advantages. It has many disadvantages, but it also has some advantages, because sometimes ideas that would not have flown there can fly here because of the distance.
Yeah. So would you like to suggest some books for young audience watching right now?
Yeah. When I was in school,
Yeah.
literally school, like 9th standard, in Mumbai, in a school called Campion. Yeah. Very good school called Campion School. There, I found, actually, which was recommended to me by Mustansir Barma, the theoretical physicist, this book by Wheeler and Taylor on special relativity called Spacetime Physics. The recent editions of this book have a third author, Wheeler, Taylor, and somebody else. I can't remember. But the time I read it was just Wheeler and Taylor. And that book, I just loved. I just loved it. Through my 10th standard, I read through, I worked out all the exercises. And I have to say that even today, when I'm doing something that requires the formula of special relativity, I think in the way that I learned to think through that book. What was special about that book was that it didn't require any detail, any higher level mathematics. Never used calculus. It never used it, just was clear and simple and completely correct. Not dumbing it down, but always in a simple way. It was just great. So this is a book, I think, if you've got school or early college people, I really recommend this. It's a fabulous book. Okay. Let's see. What else? There are, of course, the Feynman lectures on physics, which I very much enjoyed, which I'm sure many of your viewers know. Yeah. The, the At a slightly higher level, the textbooks of Landau and Lifshitz, several of them, especially classical theory of fields, uh, classical mechanics. I remember when I was in college, I started trying to learn general relativity. I was attending a course in Kanpur. It was just not making any sense. Everything felt uncertain. I remember going to my professor and asking him, okay, I read that the distance between Andromeda galaxy and our galaxy is whatever, 2 million light years. What does it mean? What does it mean given general relativity is so uncertain? What does it mean? And, I felt really unsure. And then I started reading Landau Lifshitz. The last part of classical theory of fields is on general relativity. It was just so great. I would read a part. I'd put the book down and think. And then I would have certain questions. And then I would open the book, and the next sentence would be, the reader may have the following question. It's exactly what I was thinking about. It really felt like he was talking to me. And it felt so great. I really understood it, really loved it, really appreciated, and thought the way the theoretical physicists think. So I'd really recommend those books. For quantum mechanics, there's a great simple textbook by Cohen Tanoji. There's this 2 volumes of quantum mechanics by Cohen Tanoji. My professor in IIT Kanpur, fantastic professor, A.P. Shukla, introduced us to quantum mechanics through this book. And again, fantastic book. Really something I recommend to a starting student. Okay. Now you wanted recommendations on pop science and so on. Unfortunately, I haven't read pop science since I was in school, and that's very dated. So nothing really stands out. I read many standard things, 1, 2, 3, Infinity by George Gamow, or that kind of thing. But it's probably so old now that for this new generation, there's much better stuff. I won't try to recommend.
So it's been a long time since we won, like I will not call it won. We have been awarded a Nobel Prize. So why we are not able to produce such scientists? I
Yeah,
mean,
good question.
we have theoretically good work, but Nobel Prize doesn't go to mathematical people,
Yeah,
go to physics people, experimental.
yeah,
Like you need experiment to prove something. You just cannot win because you have done some great mathematics.
yeah. So let me first say that along the lines of what you just said, that Ashok Sen won the Breakthrough Prize. This $3 million. Yes. And um, within the community of theoretical physicists, that is, arguably almost comparable in prestige. We have at least one person who's won something very big. It's not a Nobel Prize, but very big. Okay, just to say that that's an existence proof. Okay, but why are we not winning Nobel Prizes? This I don't know the answer to. I don't know the answer to. I also find it very disappointing. We're not doing it. Why are we not doing it? Yeah, somehow, somehow, somehow.
The environment,
Well, I suppose maybe, 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 maybe,
because I have
maybe.
seen people don't like to collaborate with each other much here. Rather than if you look at Europe and US.
Really? Okay. In TIFR, people collaborate a lot. I mean,
Yeah.
okay, maybe.
But other than TIFR, because there are very few institutes in India which are really doing great. But other like central universities and state
Yeah,
universities, they are really behind.
yeah, exactly. I think you hit it. I think that the thing about the US, for instance, is this. That in the US, there's Princeton, Harvard, Stanford, Caltech, MIT. Okay, they're the top places. And they're really great. But even if you go beyond the fancy places, places that are smaller, I don't know, University of California, Santa Barbara, or, less immediately prestigious. Yeah, exactly. You did. UT Austin. There are so many places that are not fancy in the sense that they don't, in novels, they won't appear as, exemplars of academic excellence, and yet they're all totally fantastic. You go to a physics department there, people are totally fantastic. There's really good work happening, and you'll often find Nobel Prize winners at these places. So the thing about the US is its depth of its academic system. Okay, that you have these fancy places, but then you've got many other places and many other places and many other places, and in all of them really good stuff happens. Okay, so there is a huge ecosystem. There's a huge ecosystem which allows for huge growth and huge circulation. And out of all of that, in the end, come these Nobel Prizes. Now, what we more have in India is a few sort of excellent places, and then it's a narrower pyramid, and I think that hurts us a lot. I think you've hit it, that if we want to get Nobel Prizes, we have to have rejuvenate research work at our universities, which of course happens, but should happen. And that whole system, it can't be just stopped. We've really, I think you hit the nail on the head. When you look at the US, there are these fancy universities, which, become shown in movies and in novels. And then there is the next layer and the next layer, and they're all totally excellent. They have Nobel Prize winners, they have fantastic people, and you can do totally top-rate work at all of them. And this won't be 1 or 2, it won't be 10, it'll be like 50, maybe more. And that sets up an ecosystem of great breadth and diversity and quality. And then, you have a lot of people going from one place to another. Students go from here to postdocs there. They go across. That incubates in the end exceptional people and exceptional work. It's that breadth and depth of that system that makes it work. Now in India, we have some very good top places, but the pyramid is much narrower. Okay, so as you say, I feel that if we really want to work, the Nobel Prizes will come once, as you say, our state universities, national universities, central universities, the places where the ordinary students go to, not some elite places.
Yeah.
When research starts happening there, the quality improves, and then everyone gets helped by that. You see, because people move from one place to the other. That ecosystem needs to be set up roughly the way it is in the US. Once that happens, I feel Indian science will really accelerate much more. Actually, having said that, the setting up of the ICERs has been a great thing for Indian science. Yes, we mean much more of that. Much more of that, I feel.
So, apart from mathematics, what should a theoretical physics student must study?
Well, it's sort of clear. A theoretical, there's a certain canon of what a physicist should know, right? And one should try to master that canon. So what is it? Some comfort with classical mechanics, including Lagrangians, Hamiltonians, that kind of thing. Some comfort with quantum mechanics, some comfort with statistical mechanics, some comfort with the theory of fields like electrodynamics, and then after that, roughly what you like. So if you want my kind of physics, you need some comfort with quantum field theory and general relativity. So it's sort of clear. And then after that, you fly. One of the things I felt was that was a weakness in our Indian education. Though, let me say, I was educated at IIT Kanpur, which was fantastic. The education was fantastic. I had such a great time. Okay, when I went to Princeton, I was a teaching assistant. I was teaching the undergraduates there as a teaching assistant. So I got a reasonable sense of what their courses were like. I wouldn't say that was better. In fact, not at all than what we did in IIT Kanpur. So on the whole, it was fantastic. But having said that, I feel one of the weaknesses slightly a cultural weakness, I feel, is that there is emphasis on knowledge more than on doing something. Okay, so there is this feeling that you get without ever being told that you need to know a lot before you can do anything, and that hurts you. You know, why? Of course, you have to know things, but that never ends. Right? All if you're a physicist, all through your life, you're learning more and more and more, and it's a vast sea of knowledge, and you'll never know everything, and you shouldn't even want to. You have to have a general view and the confidence that you enough knowledge so that you can stop thinking about things and learn as you move along. That's what I feel.
Yeah, so I think if you could change one thing about graduate school, what would it be?
Graduate school. If I could change one thing about graduate school, what would it? Yeah. If I could change one thing about graduates, I would say that um, I'm interpreting your question this. I'm interpreting your question as what element in, let's say, the Princeton PhD program that I liked do I not see in the TIFR PhD program? Okay, let me say, okay, I feel that the um somehow people in Princeton came out knowing more about things they were not working. Okay. I mean, I think that the PhD students in TIFR are totally fantastic on the average. And some of them do exceedingly well. Very intelligent, very smart, really great, and they do really well. Um, However, I feel that um, often they do really well in what they're doing, but don't know enough both around it and certainly not in very different areas of physics. Somehow we got more of that there. I think part of that is just what I first said, that people are coming through all the time. They're coming through, you go to an interesting talk on something different, that molds you. Having said that, we try very hard in string theory in TIFR to have many talks. Our talks are eclectic of various things. So the string theory students, at least those who are interested in, who want to, are able to get to some extent that kind of view. And there's we try very hard in many other ways. We go for lunch together. So, but the slightly broader thing, how much do TIFR string theory PhD students know about particle physics? Almost nothing. How much do you know about condensed matter physics? Almost nothing. That slightly broader thing, I feel, is what I would try. I don't know how to change it, but that's what I would like to. I think that would be nice to have.
So, what advice you give to students who love physics but feel uncertain about their future?
Okay. I would say the following. I would say um, that there are two things that are important. A, that you have to love physics. B, that you have to be good at it. You have to feel that you're good at it. Okay. And about being good at it, I don't mean that you have to have got good marks or anything like that. I just mean that you have to feel that that physics speaks to you and you can speak to it. It flows. Both are needed. It's not okay. If the answer to both these questions is yes, you love it and you feel that you can you can run with it. Then there is a very good chance that and you feel that this is what you want to do. I mean, there are many great things you can do in your life, and this is just one of them. But if you feel that this is what you want to do, then you can have a really good life as a physicist. And let me explain what I mean. In many different ways. First, I feel every day I go to office, the days when I have to do some administration and I don't end up thinking very much, I come back, I feel a bit low. But most days I come back feeling I've understood something I didn't know. I made progress in something I've been thinking about before. I feel really good. So every day is a challenge. It's something different, and it's just great, I think. Okay, so it's a great life. Okay. Second element of it is this, that as a professor, you make your own rules. You don't have a boss. And this is a luxury in ordinary life. Like, let me say, my neighbor. So my children were very friendly with the neighbor's children, and at some point, my children and the neighbor children, we went together to TIFR. As one of the children was, she's now big, but then she was a little girl, and I was taking her around the office, and then she asked me, "Where is your boss?" And I said, "I don't have a boss."
I'm
She
my
couldn't
own
believe it.
boss.
Yeah, she couldn't believe it. Because in her view, there is always a boss, and the boss is the one who tells you what to do. So the fact that you make your own rules is really a luxury. And then there's the global element of it. We travel. Physicists travel. If you're doing well, you'll travel. And you're part of a global community. You meet people all the time from all over the world. You name, in 50 different countries in the world, if you name the country, I would have a reasonably good friend who, yeah. So that makes it a very good life. So while the money is not enormous, you live a very good life. So, I mean, yeah, I think that it's a real, it's something.
So thank you so much, sir. This was really insightful, and I personally learned a lot.
Thank you, Ayush. Thank you for thinking of me, and thank you for. Okay, goodbye.